Humanity has confirmed more than 6,000 exoplanets so far. That sounds enormous until you zoom out. Our galaxy contains hundreds of billions of stars, and planets appear to be common around them. So the worlds we've found are not the map. They're a few bright pins on a map we've barely started drawing. And here's the twist. We keep asking, is there another Earth? But a better question is Earth actually the best version of a habitable planet? Earth is beautiful, but it's also fragile. One biosphere, one civilization, one home star, one planetary system. If you want a future that survives centuries or millennia, you don't just need a planet that's habitable, you need a planet that's forgiving. So today, we're doing something different. No hypothetical moons, no invented worlds, only discovered exoplanets, real targets, especially those in or near the habitable zone, where liquid water could be possible under the right atmospheric conditions. We're going on a journey to 4 real candidates, not guaranteed Earth 2.0, not confirmed paradises, but scientifically serious worlds, each testing a different problem in the story of habitability. Let's begin. World 1. TOI 700e, the Quiet Star candidate. Our first stop is a planet found by NASA's TESS mission. It's called TOI 700e. It's close to Earth in size, likely rocky, and it sits in the habitable zone of a red dwarf star. Now, red dwarfs are complicated. Their habitable zones are closer in, which makes these planets easier to detect, but it can also be dangerous. Many red dwarfs flare, violent outbursts that can erode atmospheres, smash molecules apart, and slowly turn a promising planet into a dry, airless rock. So the phrase habitable zone doesn't guarantee a habitable world. It only tells you one thing: the temperature could be right. What makes TOI 700e compelling is the possibility of a calmer environment compared to many highly active red dwarfs. And that matters because habitability is not just about temperature. It's about whether a planet can keep the 3 ingredients that make habitability real: air, water, and stability over long time spans. A planet can be perfectly placed and still fail if its atmosphere can't survive. So TOI 700e represents something we desperately want to exist, a temperate, rocky world that might not be constantly reset by stellar violence. And there's another advantage. It's not a lonely dot. It's part of a system that gives scientists context: multiple planets, one star, a comparison set. That's how you learn what protects an atmosphere, what destroys it, and what survivable really looks like. So is TOI 700e better than Earth? Not because it's guaranteed to be comfortable, but because it's the kind of world that could shift from candidate to characterized as our tools improve, where we stop imagining and start measuring. Distance from Earth, about 102 light years. That's far for humans today, but close enough to become a prime target for atmospheric study this century. Now we go to one of the most famous planetary systems we've ever found. TRAPPIST-1 is a strange kind of miracle. 7 rocky planets packed tightly around a small, dim star. And among them, TRAPPIST-1e stands out as one of the most compelling candidates. It's roughly Earth-sized, likely rocky, and positioned where temperatures could allow liquid water if the atmosphere cooperates. But this world forces you to upgrade your mental model of habitable. Because TRAPPIST-1e orbits so close to its star that it may be tidally locked. One side faces permanent day, one side faces permanent night. At first, that sounds like doom, but it isn't automatically. If the planet has a thick enough atmosphere and possibly oceans, heat can be transported around the globe. Winds move warmth, ocean currents move warmth, clouds redistribute energy. In some climate models, a tidally locked planet doesn't become half furnace and half freezer. It becomes something more exotic, a world with a stable, habitable belt, the twilight ring between day and night. Imagine civilization built along that band. Cities where the sun hangs low on the horizon forever. No harsh noon, no deep midnight. A permanent golden hour planet. Now, here's why TRAPPIST-1e matters even more than most candidates. Because it's not just a planet we detected, it's a planet we can study intensely. This system is a flagship target precisely because small stars make planetary signals easier to read. That means worlds like TRAPPIST-1e are part of a rare category. Habitable zone candidates that might be testable in detail. Atmosphere, clouds, chemistry, maybe even climate behavior. And this system is teaching us an uncomfortable lesson too. Some rocky planets around red dwarfs may lose their atmospheres entirely, which means the real question isn't, is the habitable zone real? The real question is which planets can actually keep air, and why? Because that answer becomes a blueprint, a map of where life can persist, where civilization could endure, and where humanity should aim if we ever expand beyond Earth. So could TRAPPIST-1e be better than Earth? Not because it's easier, but because it could be stable for far longer than Earth ever can be, if it survives the early violent stage of its star. Distance from Earth, about 40.7 light-years. If humanity ever becomes an interstellar species, this is one of the first doors we'll try to open. Transition. The habitable zone is not a promise. Before we go to the next planet, we need one rule that changes how you see everything. The habitable zone is not a guarantee. It's a temperature window. It tells you where liquid water could exist if the atmosphere and pressure cooperate. But it doesn't confirm oceans. It doesn't confirm air. It doesn't confirm stability. So the worlds we're visiting aren't perfect. They're real. They're discovered. And they each test a different survival problem. Can a planet keep an atmosphere under a violent star? Can it hold water for billions of years? Can it stay temperate without becoming a deep ocean world? Can it be close enough to reach someday and still be survivable? Now we go to the closest potentially habitable planet we've ever found. World 3, Proxima Centauri b, the closest hope, the hardest test. Proxima Centauri b orbits the closest star to the Sun. That fact alone makes it legendary, because distance changes everything. A perfect world 1,000 light-years away is a dream. An imperfect world just over 4 light-years away is a mission. Proxima b is roughly Earth mass and sits in or near its star's habitable zone. It's the nearest potentially temperate exoplanet we know. But it comes with a harsh reality. Proxima Centauri is a flare star. It can bombard its planet with radiation powerful enough to strip atmospheres, break apart water molecules, and punish surface life, especially if the planet lacks strong magnetic shielding. So Proxima b becomes one of the most important test cases in modern astronomy. If a planet can remain habitable under a star like this, then habitable worlds around red dwarfs might be everywhere. If it can't, then a massive fraction of habitable zone candidates might be dead on arrival. That's why Proxima b is so fascinating. It's not just about whether it's comfortable, it's about whether habitability is robust enough to survive the most common kind of star in the galaxy. Researchers model possible climates there under different assumptions: thicker atmospheres, thinner atmospheres, ocean worlds, dry worlds, cloud-heavy worlds, and each possibility tells a different story. So could Proxima b be better than Earth? Not because it's safe, but because it's reachable. A harsh world nearby can matter more than a gentle world far away because it forces a civilization to evolve faster. Radiation shielding, underground cities, closed-loop ecosystems, atmospheric engineering, energy systems designed for extremes. Proxima b would demand a tougher humanity, and resilience may be the real definition of better. Distance from Earth,
about 4.2 light-years. If humanity ever becomes an interstellar species, this is one of the first doors we'll try to open.
When you zoom out far enough, what does a better world actually mean? Because for human civilization, better is not just climate. Better can mean a planet that holds on to an atmosphere more reliably, a world that offers stable temperatures over long periods, a target that's easier to study so we can stop guessing, a planet with the right balance, rocky, temperate, and not drowned beneath endless oceans. So our last destination is a planet astronomers keep pointing to for a reason. World 4, LHS 1140b, the heavyweight candidate. LHS 1140b is often described as a heavyweight, a larger, more massive world than Earth orbiting within the habitable zone of a red dwarf star. And mass changes the game, because stronger gravity can help a planet hold on to an atmosphere. Atmospheric retention is one of the biggest threats in red dwarf systems. If the star is active, it can erode the air over time. But a heavier planet can cling to gases more effectively. That doesn't guarantee habitability, but it improves the odds that the planet can keep what it needs. Now here's the second reason this world stands out. It transits its star. That means from our viewpoint, it passes in front of the star, creating a measurable dip in starlight, and transiting planets are easier to interrogate. When starlight passes through a planet's atmosphere, if it has one, that atmosphere can leave chemical fingerprints. This is how we begin moving from candidate to measured, from maybe to here's what the air is made of. So LHS 1140b represents a powerful combination: potential temperate conditions, better atmospheric retention potential, and a geometry that makes it easier to study. So could LHS 1140b be better than Earth? Because it might be a planet that doesn't just host habitability, it keeps it. A world that can maintain air and water over long periods, while also being a prime target for real atmospheric detection. It's not only a candidate for life, it's a candidate for evidence. And evidence is what transforms the future. Distance from Earth about 49 light-years. Far for travel today, but close enough to become one of the most important we can actually test this worlds of the coming decades. The big picture, what better than Earth really means. Now step back. We've visited 4 discovered exoplanets in or near the habitable zone. TOE 700e, a likely rocky candidate that could be calm enough to keep its atmosphere. TRAPPIST-1e, a famous rocky world that could teach us how atmospheres survive or fail around small stars. Proxima b, the closest major hope but under a punishing star that forces civilization-level engineering. LHS 1140b, a heavyweight candidate that may be better at holding on to air and easier to study through transits. None of these worlds are confirmed to be habitable, but that's the point. We are standing at the edge of a new era, where habitable stops being a guess and starts becoming a measurement. For decades, exoplanets were dots. Now they're becoming places with climates, atmospheres, and probabilities. And once you can measure those things, the idea of a better Earth stops being science fiction. It becomes an engineering choice. Earth is not the universe's final design. It's one successful version. Some worlds may be calmer. Some may be more stable. Some may be closer. Some may hold their atmospheres better than Earth ever could. And somewhere out there, among the billions of stars we haven't studied yet, there may be a world that makes Earth look like the rough draft. So the real question isn't, do these planets exist? Statistically, they do. The real question is, which one will humanity reach first? And if we do, What kind of civilization will we become there? And if you want to explore what humanity might become beyond Earth, beyond tomorrow, beyond 2200, subscribe.